So in this one, we're going to take a look at the sum and the product of the roots. That's how we can use them. Now, one way we can use this is the following. If we have roots, can we actually build the equation? And if you look, what we have here, we have what quadratic equation has in 2 and negative 5. If we work backwards, x equals 2, x equals negative 5, doesn't it come from these factors right here? Then we multiply them together. That's where this comes from. We get our original quadratic back. Now, working backwards is nice, and believe it or not, this is using the factor theorem, which is a real cool theorem, which pre-calc will talk more about. But is there an easier way to do this? If I know the roots, or if I know properties, can I actually construct the quadratic? The answer is absolutely. Now, does this method always work? Oh, yeah, sure it does. But when we're talking about, complex roots and things like that, like 3 minus 4i and 3 plus 4i, you're going to multiply those out? No. So we're going to use this as a little way to do it. Now, in my other video, if you go, you can see the proof of this. But there are 2 formulas we're going to use. Remember, if 0 equals ax squared plus bx plus c, the sum of the roots is negative b over a, and the product of the roots is c over a. So if I know the quadratic, I know the sum and the product. Now if I know the roots, I know what they have to add up and sum when they sum and multiply to give me, which is going to be a nice little thing. Now, one of the things I've neglected to tell you is, you see when we did this, what would it happen if I decided to multiply it all by 2? Would it give me I would have 2x squared plus 6x minus 20. Does that still satisfy that? The answer is yeah, it does. Okay, so it's all depending on what number I decide to put in for a lot of times. Sometimes it's given, sometimes it's not. So you're going to see sometimes we have a choice for once. I like to make it easy as possible. Okay. So we're going to assume if we let a equal 1, doesn't it make negative b over a, the sum be just negative b, and the product equal c over a, which is just c? Okay. It's going to make things a lot easier to find the a, b's, and c's. So using the sum and the product of the roots, we're going to write the quadratic. So instead of me multiplying this beast out, which isn't too bad because they're conjugates, look what happens. We let a equal 1. So that means we have to figure out b and c. Root 1 plus root 2, oops, that's a b. That's coming from. It equals negative b over a, right? Well, we have the roots. This is root 1, and that's root 2, or root, for Mrs. Stover. 3 plus the square root of 5 plus 3 minus the square root of 5. Well, that's going to equal, we're trying to find negative b. But we've already declared what's a? It's 1, so I don't have to put anything down here. And look, isn't this super nice that, oh look, the negative square root's gone away? I'm left with 6 equals negative b. So what does b equal? It's just negative 6. So now we have an a and a b. All we need is c, and the product's going to generate that. So the product, if we generate the product, it's root 1 times root 2 equals c over a. Well, now we just need to multiply these. Now the advantage is, guess what's going to happen on these? They're always going to be nice because they're going to come out to be conjugates. Where a is 1, so I don't have to put anything underneath it. Then you FOIL this out, and you're going to get 9. The middle terms go away, minus the square root of 5 times the square root of 5 is just minus 5, which is 4. So the real question is, what's the final answer? Well, that is what we got to get. So a was 1, so it's x squared. B was negative 6, so negative 6x. And plus c equals 0. That satisfies that. Now if I did a 2, it would double all of these, wouldn't it? If I put a 2 here, wouldn't it multiply this by 2, and then you can see how it would change these to all different forms. Okay, so we can build our equation from the roots. Instead of me trying to multiply x minus 3 plus the square root of 5 and x minus 3 minus the square root of 5. Now look at that multiplication. Do you know that comes out to that? Yeah, exactly. And then we get complex, even worse. can we find the sum of the product of the roots for this? Well, the answer is, I don't. Could you find the roots and add them and multiply them? Yeah. Or isn't a equal to 2? In this case, notice how I don't let, because I'm not building. I already have it. So a equals 2, b equals 5, c equals 8. So negative b over a is going to be negative 5 over 2. That's my sum. And c over a, which is going to be 8 over 2, which is 4. That's my product. No roots necessary. That was easy to find. Okay. Let's continue to build these wonderful polynomials, because that's what we like to do. If I have a half and negative 2, not too bad. We can work with it. Now let's be smart. If I want the roots to be a half, I probably want a fraction. All right. So if you want to, we can let a equal 1. That's fine. We may get a fraction. So let's see what happens. If we let a equal 1, we're going to have, looking at this, root 1 plus root, why do I have to keep writing b? Root 2 equals negative b over a. So it's going to be 1/2 plus negative 2. Now if you look, equals negative b, right? So this is, do not, okay? Do not write the following. Negative 1/2. Okay? I need to write it as negative 3/2. Okay? Equals negative b. So that's just b. Now, wouldn't it have been smarter to choose 2 to be the bottom, a equaling 2? Then this would have been a 3. We can fix that later. I'll show you how. So that's what my b equals. What does my c equal? Well, that's from the product. 1 times root 2 equals c over a. Well, a equals 1, right? So 1/2 times negative 2 equals c, which is negative 1 equals c. So my polynomial is 1x squared plus 3/2 x minus 1 equals 0. Now, if it says to write it without rational roots, what would I have to do? If I wanted it as integer coefficients, you could also write it as 2x squared plus 3x minus 2 equals 0. How did I do that? I multiplied it by 2. Both of them satisfy this condition, just to let you know. Now, let's talk about imaginaries. This is why we like it. Look what happens when we talk about imaginaries. Well, we'll use the same product in sum of the roots. We'll let a equal 1, because I have no idea what to go with, right? So if I add the roots together, root 1 plus root 2, it's negative b over a. Well, 5i minus 5i plus a negative, right, is 0, equals negative b over 1. So what does b equal? 0. That's easy. If we take a look at the product, 5i times negative 5i, that should equal c over a. Well, c over 1, right? Negative 5 times 5 is negative 25 I squared is negative 1, so 25 equals c. It doesn't look too bad. Look, it's x squared because a was 1, plus bx, well there's no bx term because it's 0, plus 25 equals 0. And isn't this one we could solve by moving the 25 and then taking the square root? Doesn't that give me plus minus 5i? So you can see that. Now this is the last version of it. If one root of the quadratic is 3 plus 2i, what's the other root? We said this before, and I'll say it again. When you get a complex root, you get the second one for free. It's always its conjugate. So root 1 is 3 plus 2i. What is root 2? It's conjugate. Conjugates, they always come in pairs. All right, so now I can actually do this. So now let's write that quadratic that it comes from. So I have my roots. We'll let a equal 1 again, because that's our choice. So the sum of the roots is just negative b over 1, negative b over a, negative b over 1. So 3 plus 2i, and plus 3 minus 2i. Oh, complex parts went away. We get 6 equals negative b, so b equals negative 6. This will always happen. If you got imaginaries left, you got an issue. If you multiply them, 1 times root 2, it's c over a, right? Well, let's multiply them. 3 plus 2i, 3 minus 2i equals c, and then a is 1. Oh, they're conjugates. They'll multiply nice every time. You should not get any imaginaries. 3 and 3 give me 9er. The outsides and insides are gone, so it's minus 2i. And that 2i and 2i give me 4i squared, which is going to turn into plus 4, so it's 13 equals c. So then my final answer is x squared minus 6x plus 13 equals 0. And that's the quadratic that satisfies that. All right, we can continue to practice. If you have one root, we can also do that. If one root is 4, can you find the other root? Well, you just got to see what they give you. Oh, look, what's a in this case? 1, right? What's b in this case? Negative 6. No, don't I have 1 plus root 2 equals what? Negative b over a. Do I have the pieces? I have a root, 4. Got that? Got that. Root 1 plus 4 equals negative 6 over 1. If you look, if I have a little info, I can get so much from it. Equals 6. Does this root 1 or root 2, whatever, it's arbitrary. What does it have to equal? 2. We can do the same thing here, but this time I don't know anything about b, so I need to use the product. So we'd do that if we had more time, but you can see it's a simple thing we can use that can find and generate our quadratics or our missing roots. You see what you got, and you can see how you can use these two formulas. Later, guys.